Hey everybody, this is Larry. This is me going with Q4 of the bi-weekly Countdowns 136. Time taken to mark all notes. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. So yeah, this is a Q4. This is a hard problem. So definitely some of the concepts that I would talk about, I maybe take for granted that you would know. So yeah, definitely. But I think the concept on this problem is not that bad after I kind of add some visualization. So definitely, even after you understand what I'm saying, try to implement it yourself before looking at my code, because I don't think that, I think with the visualization, it'll be pretty okay. So to go over this problem a little bit, this is kind of, you have all these things about one node adjacent to it, but keeping it, the key, or one first observation that I made is that this is a tree, right? So if this is a tree, it will always kind of like spread, like almost like a, one step at a time, or one node at a time. Of course, it may take either 1 second or 2 seconds, but one node at a time, right? So we just kind of go like a breadth first search kind of way, right? Okay. Yeah, so that's the first thing. So this at least one is a little bit odd, but So one idea from that is that you can brute force from every node, and that'll give you the answer. And of course, that'll be correct, but not good enough for this problem because n is 10 to the fifth, and if you do a breadth first search from each node, that's going to be n squared, and that's going to be too slow. So what is the key idea behind this one? Is this idea called tree rerooting, or I call it tree rerooting, and I also want to give props to Gia for reminding me of this name, because I did it during the contest, but I just forgot about the name. But okay. So what does that mean? So the idea here is just, I think there are multiple ways to do it. I don't know what I just clicked on. Oh, I opened the image in a new whatever. Okay, fine. Okay. So say you have this node, and it could be more complex for sure, right? But the idea is pretty simple to understand, hopefully. Is that I do we'll go over the code afterwards, but I'll go over the idea, right? So basically the idea is that, okay, well, we can do it with two depth first searches, right? The first depth first search is just to calculate, okay, from this node, what is the furthest from each branch, right? And that's basically it. So here, I'm going to be a little bit lazy with the math, but you go this way and this way and this way. So then now, after that, then this will give you some number. Let's say this is 3, this is 1. So then from 0, then I guess one reduction to say is that now you have a tree and you're spreading it node by node. You're trying to the equivalent of this problem is to figure out which is the furthest node from this point, and from with this metric, and from the 0 node it makes sense. On the left side the smallest is going to be 1, or the largest is going to be 1. The farthest from the right side is 3, so you take 3 and you're good, right? The problem is that, and of course you can solve this recursively, as I said, with a search, and this is just 3, but this is because maybe this is 1 and this is 2 or something, and then this costs 1 to go back up, right? I don't know, the numbers may not be right because I'm just kind of, it doesn't really matter, right? That's not the hard part about this problem. I'm sure you can do an if statement, but of course now that you have here, and you're able to solve this recursively, let's say, you only need to do it once from node 0, then this is straightforward, right? Because this is a problem that you can solve on Leetcode. You just do it recursively, because the farthest from 0 is going to be the farthest from 2 plus the distance, plus this distance, and then the farthest from 2, right? Okay. I know that I'm going a little bit fast here, but as I said, this is pretty fundamental, pretty, just this part, right? It's fundamental. It is something that shows up on Leetcode a number of times, and there are a couple of problems on Leetcode that uses this idea, so definitely practice that first. Of course, like I said, if you try to do this for every node, that's going to be too slow. So then the idea behind tree rerooting is that And it's just a fancy term. I don't even remember the term until Gia reminded, or I had to ask him because I forgot. I knew that he knew. But it's just this idea that, okay, let's say we can reuse everything, right? So let's say we're rerooting, which is the term, from 0 to 2. Let's say we're trying to get the answer of 0 and then reuse it for 2. What happens, right? Well, 2, we notice that we already have the answers for this subtree and this subtree, right? So then now we're trying to figure out, okay, well, there's only one more subtree from 2, which is this subtree, right? And here, let me draw the circle slightly better. And here, I mean, the left side and the right side, the 3 and the 4, we already have the solution for these things, right? We already know these solutions because we already calculated as the part of the other recursion, but we just have to figure out this part. And this part, it turns out, right? And you could kind of, after this visualization, hopefully it's already giving you ideas, but it's just saying that, okay, well, the max of 0, so the going this way, you want the max of 0 that is not this path, right? So basically, if 0 has, I'm drawing extra children, so if 0 has many children, you still want the max of 0's children that is not this path, right? And that's basically the idea. And then now, if we're able to calculate this, and we'll go with implementation, but this should give you an idea to at least start implementing, is that then now, the answer of 2 is just the max of its own children, plus, or not plus, but the max of that, or the max of 0's children, not including 2. Okay, that's really the visualization, and I probably could have done this faster, but I was just taking it slowly. Anyway, yeah, so definitely with that visualization, like I said, take a time to pause if you haven't solved it, and try to implement it as best as you can. It's good practice. Honestly, even I need more practice here. That's why I was a little bit slow. I was just a bit rusty, right? Okay, so yeah, so the first search. Okay, so first we do a adjacency list. You know, we convert to adjacency list. This is pretty straightforward in this is an adjacency list. This is pretty straightforward. You need this for a lot of graph problems, so hopefully, you know, I don't have to go over it. But yeah, and then this part is just a regular depth first search part, right? This is to get the two things that I would remark, right? And the way that I set this up is more pre-processing, but this function actually returns the max distance from node 0, right? Because we start at 0, parent -1, and we return m, where m is the farthest distance of all its children. But the thing to notice is that the two things, I suppose. One is that we save the children down with the node that it goes to. So for the current node of node, we have re, right? Okay, so that's fine. And the second thing is just the distance metric. I wrote it this way. You could write it with an if statement, but basically the node you're going to is re. So if re is even, then this function is going to be 2. If re is odd, this function is 1, which is what the problem tells you to do, right? X minus 1 and x minus 2. Okay, so yeah, so this is pretty straightforward. I mean, I don't say that as an issue, but like, in order to solve this part should be straightforward, because if this is not, you have work to do. With, you know, that's just the way it is. I mean, yeah. So this is get distance, get max distance, or recursively pre-process the max distance from 0 with children, right? So that's basically the idea. And then the tricky part is this rerooting part, right? And I have a lot of print statements because I had some typos and mistakes, but yeah, I don't know why. I thought I did it the other way, but I think I just confused myself. But nonetheless, because I think you could use heap. Oh, because I wanted to do tuples, that's why. But yeah, this is the tree rerooting, or that's what I call it. I think it's called. I don't know if it's rerooting or tree rerooting, but But yeah, okay. So the idea here is that now we want to pass in one more variable, and that variable is the furthest. Basically, you can think of, I mean, node and parents, I think I don't have to describe it, but furthest is going to be the furthest path coming from the node, from the parent's side, right? So basically, if you kind of think about this function, then now this is has everything we need, right? Because we already have children processed, so that means that for each node we have all its children, and then the farthest from the parent, right? So then then it's just about combining them together. You can do an n largest on this because you only need to get the two largest. So this makes it n log n a little bit inefficient, honestly, but it shouldn't matter that much because the total number of children is going to be linear, right? So this is in the worst case n log n. So I'm not going to worry about it, but you can reduce this to O of n if you're a little bit more careful, is what I want to do. But yeah, but that's basically yeah, this idea. And I chopped it at 2, and the reason why we chop it at 2 is because basically we want to get the max element, right? From the children. Okay, this is the idea that I didn't talk about and that I thought I was going to cover a little bit. But okay, let me bring up the visualization real quick, in case you didn't figure this out. Yeah, so basically, as I said, actually, let's bring this. This is fine. So basically here, we're still looking at node 2, right, in this visualization. And the idea here is that the furthest node going up the parent's path, we have to look at 0's children, right? So, oh, no. Oh wait, I think I'm conflating two things. Let me sorry, let me go back. Let's ignore this for a second, or at least this part for a second, right? Then now, the answer for the current node, I wrote this in a weird, or maybe not weird, just different way. But yeah, the answer for this current node is going to be either from the parent, which we got, right? This is the way that we did the math, or the max from its children. So hopefully this part makes sense so far for getting the current node, right? Because the furthest is just the furthest path coming from the parent, and here we just get, we already sorted this, so we already know what the max is. So that's what this thing is for, right? It's for one of its child, the max node. So it's just one of those things. So you have the max of like all its child or all its children and or the parent. Hopefully this part is pretty reasonably straightforward. Yeah. Okay. Right. So then, what is this part? This part is a fancy way to update furthest for the child. That's the key part about this, and also just doing it recursively, right? So okay. So again, hopefully this part makes sense. We're just traversing the node. So here, what we want to do is calculate the furthest going down to the child, right? And here, this is where I'll bring the visualization back up, right? Is that okay? So now we're going from 0 to 2. We're going from 0 to 2 recursively, say, and we want to update the furthest, right? Well, it turns out that in this case, yeah, if we're going to 2, we have to get the max out of all its other child. So then, obviously, if you do a linear thing, like if you do a min of all the linear, and maybe you do a for loop, and do a min over all the other children, filtering out the 2. That's gonna be too slow, because if you have, for example, you have a graph that looks like this, or even, I guess that is the graph, and you want to do it for each node, that's just going to end up being n squared, right? So for 4 children, you're going to do 3 operations for each one, so then it ends up being n squared, which is too slow. the key observation is noting that, well, in the pigeonhole principle is that the max is either, it's going to be one of the two values, right? It's either, if you're going from 0 to 2, the max of all the children will either be 2 or not 2. If the max of children is 2, then we can get, just do the math on the rest of the children, which we already have done. Or if the max is not 2, then it's just the max of everything, right? Because we know that 2 is not the max. So that's basically the idea that I have here. So that it basically optimizes it. That's why we did the sorting by 2 and get the max 2 elements. Because basically, yeah, and we do the math. So we have the 4 is equal to 0, right? If we have any children, and we should, because we're going down one of them. I don't know why I wrote it this way. I guess I just didn't want to think during the contest. But yeah, if the node is not V, then we can take this one for the max. If the node is equal to V, and we have a second child, then we take the furthest here, right? And that's basically the idea. We take the max or the second max, depending if the max is the current child that we're going down. And also we just max it by the furthest, right? Because that's the incoming parent, so it could also be the parent as well. If you want a visualization on this one, which I did not do here, it is basically saying that if you have something like this, right? Right, and this one, and you're going. Okay, let me change the colors real quick. Right, and you're going from this node going to this node. Then now it is going to be the max of all the children in some way, not including this one, right? In the way that we already talked about, or of course the parent. And of course the parent cannot be this child, so that's why, so yeah, so you have to consider all those paths. And once you have this visualization and this idea, it all makes sense. And this is just the path cost, right? That we got from the problem, which is here, right? That's the path cost. And that's pretty much it. Yeah, this is called tree rerouting. I don't know if you could Google for it. It's not an idea that comes up that much, but apparently enough. But yeah, and that's pretty much it. And yeah, so what is the complexity here? Like I said, if you do a proper n largest with a heap or something like this, or even just with if statements and a linear scan, it's going to be O of n. So because this whole function is O of n, you can think about this as just looking at all the children, and then we go down all the children, so it should be the same. And then this is just if statement, right? So this is a regular depth first search. This is of course obviously a regular depth first search, so this is linear. So if done correctly, the entire thing is just 2 depth first search, linear time, linear space. However, the way that I did it, because I used sorting because I was lazy on the typing, on correctness, this is going to be n log n. Why is this n log n? Because this is the summation of all the children, and we only have at most n child, or n children. So this is going to be n log n, or sum of the n log n's, which is also just n log n. And yeah, and that's pretty much it. Yeah, that's all I have for this one. Let me know what you think. Thanks for watching. Yeah, and you could watch me solve it live during the contest next. Nope. Another wrong answer. Okay, only one wrong answer, which is actually not as bad as I expected for me. Okay, time to mark no notes. We could solve this probably, hopefully. Yeah. Yikes. Wasn't that bad, but I just kind of, I don't know, mind froze on it. Okay, tree edges, okay. A node for each node I. If it's odd, if it's even, so okay. Yeah, I don't know why I don't know how to solve this yet. I'm just kind of setting it up. I didn't know that actually gets an answer. Okay. 10 to the 5th. I really should have gone Q2 faster or 3 faster, but I am just being dumb. Oh well, took so long on that one. Alright, I mean, this seems like just DP. Wait, maybe? What is the output again? Is the time when all notes, if you mark, oh, I, not just 0. Okay. So basically when everything is done, right? So it's y00, so it'll be 2, okay. Y is equal to 1. And I'm not awake enough for this. Okay. I mean, it's a tree, so this at least one node is kind of weird. So we have to do at least one per first search, maybe, but. People are getting that though. I'm just thinking a bit slow. So, what is the odd even thing too? Okay, so let's say you have a breadth first search. Okay, let's actually understand. So even means that it can only come from one node, right? From that way. I mean, okay, so that's gonna be n squared if you do it. Okay, so we have a tree, so now we have to pre-process this. Right. Oh, the last node, the furthest node from this node. Yeah, okay. Where we have a star graph, Larry. So it's a, whatchamacallit, a tree recompoing. Okay, fine. Yeah, okay, fine. How would this look like? So then now you get all the answers. No, that's not what I'm going to do. Okay, so you store all the children, right? And then you have the parent. So you have to do time, right? So okay, so right, so if it is even, if I is even, then so that means that if we is even, then it's this time plus 2, right? Okay. I'm writing it like a new, but that's okay. Okay, so then now we have to for this. Alright, let's just write it out. And it's just like this. Okay, and then now near, far, wherever you so now. Is this right? No, that's not right. I mean, that's what I wanted to be right. But man, I'm not. It's been a while since I practiced this idea. Okay, so now you fill out the tree first. Oh yeah, okay, yeah, fill out the tree first. Okay, fine. Yeah, I'm slow on this one. This shouldn't be that bad. Okay, so 0. That's not quite right. I don't. So this is 1, then. Oh, whoops. I put it here by accident. Well, not by. I don't know if it's by accident, but either way. Well, I had it the other way, I suppose. Oh, there's no 2. Okay. Is it asymmetric? Is it symmetric though? Because now you have to go, let's say you go in the other direction, it's not the same, right? That's fine, yeah. That's just, okay. What is top 2 again? It's like a heap thing, right? Heap Q, top 2, min 2. Always forget. N largest. Oh, it uses just sorted anyway? That's what heap does? Oh, equivalent to. Maybe that's not right. Okay, fine. Oh, but you actually need to know the values, right? Okay. I'm so bad at this. Two, 1, okay, I think that's right actually. So then now Okay, that's good. Is it? Yes, okay. So that's index. Okay. So now to renode is equal to value sub 0 sub 1. What if there's no other values? Would it always be other values? I guess so, unless there's one node. Maybe. I don't know. No, this could be a leaf, Larry. And then this would never get caught. Alright, let's just work on it, get a wrong answer, then that's fine. Yeah. Okay, but then now was this, but then it's gonna be whatever, let's just write it this way. And then plus 2 minus no minus no. Okay, so then now you have either the farthest or close 46343. This is wrong, but okay. So okay, 0 1 is wrong. Why is 0 1 wrong? No, after you call the function there. 0 1 sounds right. Is going in the other direction, maybe, that I don't combine correctly. So it was 1 2, I have 1 3. Okay, why do I have 3? 3 is because I have half an hour. I should be able to finish this, but okay. So the 4 is coming in as 3, that's why. So going from 0 to 1. That shouldn't be 3. 0 has no other further, so this should be 0. Right? Probably not, but yeah. Oh, because it's greater than 0. Also, this is just like okay. So yeah, okay, so maybe this is if okay. That's more closer than I expected, to be honest. Yeah, okay, that's not right either. Oh, because I have to do the math here instead. Silly. Okay, 1, 2, 4. Okay, so this is wrong still though. Which is not great, but maybe we're making progress. I don't know, are we making progress? So 2. So 2 is 3, that's right. So we want 4. Why is 4 5? 4 parent is okay, so input is 3. Is that right? For 4? I don't think so. Why? Tell me why. There's no child, that makes sense. So why is it 3? So 0. Oh, I see. It has to be the 4. It has to be from that branch as well. Okay, fine, that makes sense actually. Okay. Am I ready? Alright, YOLO 243. Let's get the inputs correct. I feel like I keep getting wrong answers from the inputs. Yeah, okay. Not that bad, but slow Q3. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this contest, these problems, my comments, everything in between. Stay good, stay healthy, to good mental health. I will see y'all later, and I take care. Bye-bye.